we will be discussing about p-n junction diode, that is working of p-n junction diode and its function uh, and its utility practical circuits. So basically what we understand from p-n junction diode, if we take a p-type semiconductor and n-type semiconductor together, and if we join like this, if we take p-type semiconductor and n-type semiconductor, as we know that when semiconductor is formed, initially we will be getting it is either fabricated as p-type or n-type. To fabricate p-n junction diode, we take different concentrations, that is hole concentration and electron concentration. In p-type semiconductor, we will be having concentration of holes as higher concentrations, and the n-type semiconductor, as we know that we will be having electrons as a majority carriers. Here we have electrons as majority carriers. Similarly, in p-type semiconductor, the p side, we have electrons in minority carriers. Similarly, the n side, if we see, the n side will be having some of the holes as minority carriers in n side. So as soon as we join p-type and n-type semiconductor together, what happens if we consider this as a junction, this is as a meeting point of p-type and n-type, and if we compare the concentration of charge carriers, the left hand side and the right hand side, so what we can observe, the right hand side we have the concentration of holes as higher, fine. Here we find large number of electrons in n side, and we find only few electrons in p-type material. So what happens, as we take a reference as this line, if we take a reference, what we can see, the left hand side, this side has less concentration of electrons. So due to concentration gradient, that is one side we have higher concentration, another side we have lower concentration, so it makes concentration change in concentration, which is called concentration gradient. So the charges will have the tendency to move from higher concentration side to lower concentration side. So what happens, these electrons will try to move towards the p side, and at the same time what we can see, due to concentration gradient, what happens, this electrons will move from n region to p region, and similarly we can see in case of holes, the holes actually the holes does not move, its position only changes, but practically for understanding what we say, the holes is moving from p region to n region, but it's only the position will change. What is that positioning change? If we see the structure of silicon 1 2 3 4, we have, this is the outermost orbit electrons, this is 1 2 3 4. Similarly, we have another silicon like this, we have another silicon structure. So if I take this 2 electrons which is in covalent bond, these 2 electrons in the covalent bond, and suppose one vacancy creates here, at this position, that means when these electrons from this position, the electrons is releasing by receiving some energy, the holes generate at this point, fine. So what happens once the vacancy is created at this level, very close to this vacancy, this electron, this particular electron will try to occupy this vacancy place. So what happens, these electrons will occupy this place, and at the same time the holes will be generated here. So that's what we say, that initially here we had holes, position of holes, and once the electron is occupying that place, the holes position is shifted to another location. So by this phenomenon it will work. So as soon as these electrons is crossing the junction, this is crossing the junction, what happens, we have to understand which forms a depletion region in between p type and n type. So as we know that the depletion region is a combination of immobile charge carriers, that is electrons and holes. So that formation, how it forms, that part also we have to understand. So let us talk about the formation of depletion region. So once we talk about the structure, once we talk about the structure of p type and n type, formation of depletion region. So here we have p type, here we have n type. So n type material is your pentavalent impurities atoms, which is here. The pentavalent impurity atoms, I am just drawing the structure. If I take a phosphorus as a pentavalent impurity, so it will have 5 electrons in the outermost orbit, because the phosphorus has atomic number, that is 15. So in first orbit it will have 2 electrons, second orbit it will have 8 electrons, third orbit it will have 5 electrons. So basically these inner cells, that is, this is your first orbit, this is your second orbit, and here we have a third orbit. So these inner cells will not do anything, this will not play any role. So we will be avoiding this discussion about this first and second orbit. So whatever happens, that will happen with this outermost orbit electrons only. So these 5 electrons we are discussing here, 1, 2, 3, 4, and one more electron I take it here for the phosphorus. Then remaining I take as a silicon, 1, 2, 3, 4. Another silicon I take here, 1, 2, 3, 4. Here we take silicon, 1, 2, 3, 4, and another silicon, 1, 2, 3, and 4. So what happens? There will be covalent bond between silicon and phosphorus atom. Another covalent bond. Here it will have covalent bond, and here also will have covalent bond. So if we focus about this phosphorus atoms, now we can see the total electrons in the outermost orbit is total, it is 9. How we can see? How we can say it's 9? Because this is 2, this is 2, 4, 5, 6, 7, 8, and this is the 9th electron which the phosphorus is having. because as we know that the atom has the tendency to occupy 18 electrons in the third orbit, the maximum 18 electrons it can occupy. So of course the 9 electrons also can occupy, but this phosphorus will have the tendency to release this ninth electron and to make it as octet at the outermost orbit. So this phosphorus will have tendency to receive some energy from somewhere, and once it is receiving energy, even if you bring this structure at room temperature, so indirectly we are supplying 27 degrees centigrade at room temperature. So from this energy, this ninth electron which is here, this will get energy, and this electron will leave this phosphorus atom and this will become free. So once this electron is coming out, this phosphorus will gain a charge which is called positive charge. This will be now this phosphorus, as we know that the atom which is releasing electron, the atom which is giving you the electron will gain a positive charge, and the atoms which is gaining the electrons will gain a negative charge. So here, as phosphorus is releasing one electron, this will gain a positive charge. The same phenomenon happens here. So the electrons, as I say that the electrons which is coming from this region to another region, that is this ninth electron of phosphorus. So what happens? One positive ions will get formed here, positive ions. Similarly, once the electron, another electron is released from n side, another positive ions. So once the electron is out of the atoms, it will convert that particular atom as a ions, which is positive ion. Same time, here I can say at p side, the structure is having a trivalent at trivalent impurities. So if I say trivalent impurity is aluminum, as we know that the aluminum is having atomic number 13. So in first orbit 2, second orbit 8, and third orbit it will have 3 electrons. So we will deal with the outermost orbit electrons, that is 3 electrons. So the 3 electron is 1, 2, and 3. So other atoms are silicons, 1, 2, 3, 4. Here we have silicon, 1, 2, 3, 4. Here we have silicon, 1, 2, 3, 4, and another silicon here. So here it is covalent bond, here it is covalent bond, here it is covalent bond. But at this place we can say that there is no charge carriers available for forming a covalent bond, and the aluminum will fulfill its outermost orbit, that is octet, by having 8 electrons in the outermost orbit. So this aluminum will have tendency to take one electron. So the electron which is releasing from this particular atom, that is phosphorus atom, this electron will be accepted at this level here, this level. So once this electron is coming here there will be formation of covalent bond. Now this aluminum will become satisfied atom, it will become stable. But as soon as it is receiving one electron, this will gain a negative charge. So by this phenomenon, negative ions are getting formed very close to the junction, So the movement of charge carriers from n region to p region, this will be only available for a moment. As soon as there will be formation of depletion region, the movement stops. This region from here, from this point to this point, it is called depletion region. Depletion region. So now we see why the process stops, why there is no further movement of charge carriers. Now suppose if you have electrons here and it has to travel towards the p region. Now these electrons should have that much of energy to cross this junction. It has to cross throughout the junction. So now these electrons will not have that much of energy because this 27 degrees centigrade only is available there, that is room temperature. Now if you want further the movement of these charge carriers, that it has to move from n region to p region, then we have to apply external potential. Now moving to next discussion of depletion region. As we understood here how the charges are getting formed, immobile charge carriers, that is ions are getting formed. Remember that the positive ions will be formed in n side and negative ions will be formed in p side. Now these charge carriers will not have tendency to either it will borrow or donate any free charge carriers. So that's why it is called immobile charge carriers. Now as we know that once we discuss about positive ions, suppose we have positive ions and negative ions. Once these two ions are very close to one another, there will be formation of electric field. Electric field will be formed from positive ion to negative ion. There will be electric potential which will be developed. So same thing happens here. Here at right hand side we have positive ions, left hand side we have negative ions. So there will be formation of electric field, that is electric potential. It will be in the form of potential. That electric field will be approximately 0.7 volt. This is approximately, we don't say exactly because that also depends on temperature. In case of silicon structure, and it will be approximately 0.3 volt in case of germanium structure. So now if we need to operate this device PN junction diode further, so we have to apply the potential against this electric field which is developed across the junction. And that's why we say that the threshold voltage of PN junction diode or cut-in voltage or knee voltage is 0.7 volt in case of silicon and 0.3 volt in case of germanium. Thank you.